To the learning of computer networks and security. We are going to start with the module 5, that is multimedia networking. Let's discuss about voice over internet protocol. We have discussed in detail about streaming stored video concept, wherein both audio and video, how the streaming took place right from the server end to the client end, we have seen in detail. Now let's see only the voice part. So that is voice over IP. First, let's see what is VoIP or voice over IP. So here we can also call this as real-time conversational voice over internet. You can also call this as internet telephony. So it is commonly called as voice over internet protocol. Here basically we'll be discussing about only the voice part, how the sender sends the audio and how at what rate the receiver receives this audio, and what are the delays that is occurring during the transmission, or whenever the audio is transmitted from the sender to receiver, what type of delay is experienced there in the network. So all that we are going to discuss over here. So first we will just see here some of the basics of VoIP. Here it is same as streaming concept what we had already seen in video, but only thing is here we don't have the video aspect, we have only the voice or the audio part which has to be sent. So here we'll just see the limitations of best effort service. Before that, I would just I just want to tell you one basic part of this audio, that is we have a threshold. So what is that threshold? Usually the voice, whenever the sender sends, or whenever the audio that is sent by the sender, generated by the sender, okay, so after generating that, once the sender sends that audio, suppose if the delay that the audio is experiencing in the network, is less than 400 milliseconds, then such a delay is acceptable at the receiver side. I repeat, suppose if the user is, or a sender who wants to talk, is generating an audio, and after generating an audio, once the audio is sent to the network, in the network we know there will be varying delay. So the delay is maybe due to the router's buffer or the queuing that takes place at the routers, okay, or the router's buffer capacity, or in general you can say there might be a lot of congestion in the network, because of which the delay might increase, or sometimes because of light congestion the delay might decrease. Suppose if the delay is as large as 400 milliseconds, we can say the delay is acceptable at the receiver side. So receiver is able to play the audio without any without experiencing any disturbance. Suppose if the delay there, network delay, is less than 150 milliseconds, still more less, that is less than 150 milliseconds, we can just say that that type of delay is totally negligible. We can simply ignore that delay. You can even cannot use the term delay over there if it is less than 150 milliseconds. So this is one point that we all have to remember. So at least the delay minimum, the maximum the delay should be 400 milliseconds. Above 400 milliseconds, if the delay increases, then definitely the receiver end, the play out disturbs. So receiver will experience the delay there. Okay, so we'll just see here the limitations of best effort service. So we will see what exactly is this. What best can be done to send the audio without experiencing much of delay in the network. Okay, so let's take one small example here. So here we have alternating talking spurts. So what is the meaning of alternating talking spurts? It is something like we have varying talking speeds. So varying talking speeds. So sometimes we speak very fast, sometimes we speak very slow, with some pauses, with some silence at the beginning or maybe in between, right? So all these type of talks we experience usually generally in real time, right? So here for all such types of audio, we'll have to prepare for sending that without experiencing much of delay. Okay, so here we'll see what can be done. So any audio that is generated at the sender side, will be sent usually for every 20 milliseconds. Let's take an example here. For every 20 milliseconds, the sender sends the generated video. So not video exactly, it is audio, generated audio. So here let's take an example. Suppose if the sender has generated 8000 bytes for every 1 second. So what is that? The sender is talking now. His talking speed is for every 1 second 8000 bytes are generated. Now don't think that all these 8000 bytes can be sent at once. No. So what the sender is doing now here, all 8000 is not sent. His sending speed is just 20 millisecond. It is something like only few bytes out of this for every 20 milliseconds he is going to send. So how many bytes out of 8000 bytes, whatever is generated for 1 second, how many bytes of that can be sent by the sender for 20 millisecond? So that we have to generate, and that is how much it is, 160 bytes of data. So out of 8000 bytes, only 160 bytes can be sent for every 20 milliseconds. And let's call this 160 bytes of data as a chunk. So here our sender is sending chunks of data. Chunk is nothing but a small piece of the generated audio, and that chunk is actually sent as a UDP datagram, or this chunk is actually encapsulated within the UDP datagram. So what is the meaning of encapsulation? You add a header to this particular datagram, and this chunk of data 160 bytes you fix inside the payload section of the datagram, and that is how you encapsulate it, and that datagram is sent over UDP as an underlying transport layer protocol. Okay, so this is how we send the audio which is generated at the sender side. So chunk plus header is encapsulated and it is sent. So for every 20 milliseconds, such chunks of audio will be sent from the sender side. Okay, so now once this data is sent out from the sender side, what we can note here is you are now handing over these chunks into the hands of network. So now in the network there will be n number of intermediate routers, and at all these routers there is something called as queues maintained, and all these queues might be filled up, because that is not only one sender who is sending the data. There may be n number of other senders also who will be sending the data. So there will be n number of intermediate routers which has so many queues there, and that queues might be already filled up with n number of packets or datagrams sent by n number of senders there. And because of this, at the router's end, intermediate router's end, there might be traffic that is generated. So now the challenge is, we have two challenges actually now at the receiver side. So what is that? One is when to play this received chunk. Is it something like as in when the receiver receives this chunk, each chunk, whether he should begin the play out? That is the first challenge at the receiver's end. Second challenge is what to do if any of the chunk is missing. So here what is that our sender is doing? It is something like we have an sender here who is generating an audio, and say the audio is generated generating the audio is generated for every say 20 for every 1 second actually the audio is generated, but how the generated audio is sent, that is sent for every 20 milliseconds in the form of a datagram, and that datagram contains only 160 bytes of data. And now once that datagram is sent, you already know that there are n number of routers here in the network, and at each such router you may experience queuing delay there, because there may be n number of other senders who is sending the chunks there, right? So now at the receiver end, who is there now, who is supposed to receive the data, at the receiver end we have two challenges. One is when to start the playout. Suppose the first chunk is received here at the receiver side. Immediately after he receives the chunk, can he start his playout? What if the second chunk there is not obtained on time? Like at the receiver end, again for every 20 milliseconds he is supposed to receive the chunks, but for the next after 20 milliseconds, what if he is not receiving the chunk? Second chunk, what if he is receiving after 40 milliseconds? What is going to happen there at the receiver end? There varying delay. So definitely receiver will experience delay there at his end, so his playout gets disturbed. Or what if the receiver misses the second chunk? Instead of second chunk, what if he receives third chunk? So whether it is understandable at the receiver side, whether he is able to play out, and whether he is able to play there the received chunk, so it will be meaningless over there. So what to do in these two cases? These are the two challenges which we have to first face here at the receiver side. So we will see here how these two challenges are faced. So one thing is we have to now deal with this packet loss. Second thing is we have to deal with something called end-to-end delay. So we'll see each of this. What is it? So first one, it is the packet loss. So what is this packet loss actually? Why the packet is getting lost? So here, as I already said, sender sends the data in the form of a UDP datagram. So UDP is the underlying protocol here. And as we all know, in UDP we don't have reliable data transmission. So reliable data transmission is available only in TCP as underlying protocol. So what is the meaning of reliable data transmission? What if in TCP, suppose if any packet gets lost, in TCP, our TCP has a mechanism to overcome that issue by retransmitting the lost packet. As you already know, TCP retransmits the lost packet, but UDP doesn't have that retransmission policy. But what happens if in the case of audio, if TCP retransmits that data segment, retransmits audio segment, what might happen? Because of this retransmission of audio segments, there might be too much of such retransmitted audios plus original audios created in the network, and because of that there might be too much of congestion occurring at the network side, in the network. And because of this congestion that is occurring in the network, again what TCP tries to do there is, TCP will try to slow down the sending rate. We have a congestion control mechanism in TCP wherein sender will slow down the sending traffic if the congestion increases. So what if the sender's sending rate decreases? Definitely when the sender's sending rate decreases, receiver will have to experience lot of delay. He will have to wait for long for receiving the next audio. So whenever such a delay increases in the receiver's end, definitely that becomes meaningless here at the receiver's end. So TCP is not at all a good choice for transmission of audio here. So UDP itself, which doesn't have this retransmission mechanism, or which doesn't have this reduction of sending rate mechanism. So all this whenever, since this doesn't have all that mechanism, UDP is most stable for this voice or the audio transmission. That is one thing. There is one more solution that we can give for this packet loss. That solution we can call it as forward error correction. As you all can see here, FECD indicates forward error correction. So what is this forward error correction? Suppose if any packet is lost, what you do there is, along with the original packet, you send a duplicate packet. This is a precaution. When the sender is generating an audio, that audio will be sent as the original audio. Along with that, a duplicate of that or audio also will be sent. So two sets of the same audio will be sent there. And this is kind of precautionary measure. Suppose if any original or any one of the clip is lost, there is a backup there which will make up somehow, and it will somehow reach the receiver. So this type of mechanism also is possible. This type of solution also we can give here, that is forward error correction, what we call. Forward error correction is done. Then TCP mechanism also we have. Okay, so after that what we have here is the next type, that is end-to-end delay. So what is the meaning of this end-to-end delay? So end-to-end delay is actually between the sender and receiver, the varying delay, and this varying delay in the network is because of varying talking spurts. One thing, varying talking spurts means what? The sender's sending rate also, sender's speaking rate varies, and for each of that rate what the sender is actually sending the data, the sending traffic also should be adjusted accordingly, and the receiving rate also should be, receiver's playing rate also should be adjusted accordingly. Okay, so we will see in detail what is this end-to-end delay. End-to-end delay is something like, so we have several routers over there and intermediate routers. So suppose here if the delay, what if the delay is less than 150 millisecond? So if the delay is less than 150 milliseconds, it is something like which the user can totally ignore. The receiver can totally ignore this type of delay, less than 150 milliseconds. Slowly, what if my delay increases to 400 milliseconds? So this is also acceptable, but you can just say slowly if the delay increases from 1% to 10%, the receiver can tolerate such type of delays. But if the delay increases beyond 10%, that is between 10% to 30%, if the delay increases, that means if it goes again beyond 400 there, definitely the receiver will experience lot of disturbance, like what we have already discussed. And this end-to-end delay is mainly because of the intermediate routers and all n number of queues that is maintained here at the routers. And here at each queue, at each router, there it consists of too much of packets that is arriving from multiple senders. And whenever there are multiple packets there waiting in the queue, there will be all the packets there that experience delay at the queue itself, right? So here only few packets will get a chance to move over the outgoing link and to reach the receiver. So this is actually about the end-to-end delay. So next important thing is packet jitter. So what is packet jitter? First of all, what is a jitter here? Jitter is actually the disturbance. But what type of disturbance is this? It is something like fluctuation between packets, that is varying delay due to router's queuing delay. So like I already said, fluctuation, it keeps fluctuating. So what is the meaning of fluctuation? So here, suppose, let me take an example. A sender is sending two packets or two chunks of data. The first chunk of data, what he is sending, chunk 1, he is sending maybe at time t0. So initially he is sending that packet. Say after sending this chunk 1, that is after maybe around 20 milliseconds, he is sending chunk 2. Now we are trying to find out the delay here, or the gap between this chunks. We actually, what as a sender, what do we expect at the receiver send? Receiver should be receiving chunk 1, and after 20 milliseconds only he is supposed to receive chunk 2. Or that is what sender may assume, right? But actually receiver may receive in different ways. So what are those in different ways what the chunks is received at the receiver side? We'll see that. So when chunk 1 is sent, Say here there is intermediate router via which the chunk has to be passed. So this router will have a buffer along with that also he has a queue there maintained. See, this chunk 1 will come and sit at the head of the queue. Suppose if the queue is empty, the chunk 1 will come and sit at the head of the queue. And now after 20 milliseconds, the chunk 2 is arriving at this router, and by the time this chunk 2 arrives at this queue, there might be n number of other chunks which already has reached this queue from several other senders. So from several other senders and multiple other chunks might have reached here at the queue, and already those chunks might be sitting behind chunk 1. So already this queue might be filled up. So what happens in that case? Chunk 2 doesn't have any space. There are possibilities of chunk 2 getting discarded. One thing. Or maybe we'll see this last space is empty here in this queue, and slowly this chunk 2 will occupy that space, and chunk 2 is now sitting after a big gap, long gap from this chunk 1. That is, you can say far away from this chunk 1, this chunk 2 is sitting. So what is going to happen there? Who is going to get the first chance to go out? That is, chunk 1 is going to get the first chance to move out over the outgoing link, and after chunk 1 there are several other packets which has to move out, and after all those packets are gone, then only this chunk 2 will be getting a chance to move out. So in that case, what happens at the receiving end? At the receiving end, first definitely chunk 1 reaches, but after long gap chunk 2 reaches at the receiver's end. Definitely because of this long delay, receiver may experience disturbance. This is one possibility. One more possibility, you can just see here, one more possibility, the same example, chunk 1 and chunk 2 are sent in the gap of 20 milliseconds. But when chunk 1, say first it reaches the router, it will first go and sit inside the queue. Maybe in that queue, already there are multiple other packets which are sitting. So now somehow chunk 1 got a chance to be in the queue. In front of queue, ahead of chunk 1, there are multiple other chunks also. Ahead of chunk 1, there are multiple other chunks sitting inside the queue. Now chunk 2 is arriving. Somehow chunk 2 has arrived here after 20 milliseconds. Say here, within this gap of 20 milliseconds, assume none other chunks have come. So because of that, chunk 2 got a chance to sit right behind chunk 1. So what is happening? Chunk 1 is sitting inside the queue, but where is it sitting? Behind several other packets, several other chunks. But chunk 2 who has arrived after 20 milliseconds, let's assume that in this gap of 20 milliseconds, no other packets have reached this queue. So chunk 2 is sitting right behind chunk 1. Now what is going to happen? All the other packets which is ahead of chunk 1 will get a chance to go out of the queue. But after all those packets, now definitely chunk 1 also will get a chance. But we know that chunk 2 is sitting right behind chunk 1. So definitely chunk 2 also will get a chance to go out immediately after chunk 1. So chunk 1 first it will reach receiver, and after chunk 1, chunk 2 will reach at the receiver's end. So in this case, what is going to happen? The gap, initial gap was 20 millisecond, but when it reached at the receiver end, it reached back to back without any gap or without any delay there. So these two possibilities may happen, and this clearly we call it as varying network delay, or in other words, we can call this as jitter. Packet jitter. So what is going to happen at the receiver end now? When chunk 1 is received, immediately receiver will start play out. And suppose if the gap is too much over there, so for play out of the second chunk, definitely there will be big gap, right? So this is jitter which the receiver has to identify, and he should try to overcome that jitter. So we'll see what would be the solution for this particular jitter. So we have actually 3 solutions provided for this jitter. So we will just see that. So in order to remove these jitters, or the solution for this jitter, at the receiver end or at the sender end itself, we should add something and send. So what is that? First thing is timestamp. The time at which the sender has generated the chunk, the time at which the sender has sent the chunk, generated rather than telling it as generated, the time at which the sender has sent out the chunk, that timestamp can be recorded, that timestamp can be included. Second one is, for every chunk you can add a sequence number and send. Third one is play out delay. So play out delay is something like whenever the receiver is receiving the chunks, he can fix one delay there for playing the chunks. The gap between the chunks to play the chunks, that gap whatever you have between every chunks, that delay can be fixed. It is something like, at the receiver's end, if the chunk 1 is received, we will fix a delay or a gap between chunk 1 and its subsequent chunk. So what is the subsequent chunk? Chunk 2. So if this gap, if I fix, say suppose if I fix it to 20 milliseconds, no matter what time the chunks is received there, that gap you fix it as 20 milliseconds. What is that going to happen now at the receiver side? The chunks are played at fixed rate, that is at a fixed gap of 20 milliseconds. First chunk is played, after 20 seconds second chunk, after 20 seconds third chunk. So that is at every fixed rate here the chunks are played at the receiver's end, right? So that's why the receiver should be very careful when he is fixing up this delay, fixed delay. Okay, so these are the three solutions what we could give for removing the jitter. So here at the receiver end, what can be done to remove the jitter? So at the receiver end, actually, like I already said, the chunk should be, once the receiver receives the chunk with the timestamp, so what is that? Sender would have already added the timestamp and sent. So for looking at that timestamp, the receiver will come to know the sender's sending time, and based on that he can order the chunks. So the first chunk which is received with the timestamp, given timestamp, he can identify and he can start play out, and after that the second chunk also he can identify and play out. So this is what he can do. So the next solution what the receiver can give, or the receiver's end, what we can give at the receiver's end is delaying play out. It is something like same as what we had seen in HTTP streaming technique. What was that? So receiver can initially have a store of received chunk. All the received chunks he can maintain in the buffer, and after certain threshold is reached, he can fix up a threshold at the receiver's end. Once the threshold is reached, that is, you can keep the threshold as some bytes. Once those many bytes are accumulated in the buffer at the receiver's end, then he can start his play out. So all chunks are played in that case without any disturbance. So maintain a threshold and wait up to that threshold up till the bytes gets filled up till that threshold. Once the threshold is filled, you can start, the receiver can start his play out at his end. So in both the cases here, jitter will be removed to some extent.